Okay. All right, so I went ahead and decided to make the last section of video by itself. It's like 50 or over 50 slides, so I'd rather you guys could just focus on it independently. One-way ANOVA, comparing several sample means. Go ahead and look at your focus points. In our past work to determine the existence or non-existence of a significant difference between population means, we restricted our attention to only 2 data groups representing the means in each question. Many statistical applications in psychology, social science, business administration, and natural science involve many means and many data groups. Questions commonly asked are which of several alternative methods yields the best results in a particular setting? Which of several treatments leads to the highest incidence of patient recovery? Which of several teaching methods leads to the greatest student retention? Which of several investment schemes leads to greatest economic gain? Using our previous method of comparing only 2 means would require many tests of significance to answer the preceding questions. For example, even if we had only 5 variables, we would be required to perform 10 tests of significance in order to compare each variable to each of the other variables. If we had the time and patience, we could perform all 10 tests. But what about the risk of accepting a difference where there is no difference, a type 1 error? If the risk of a type 1 error on each test is 0.05, then on 10 tests, we expect the number of tests with type 1 error to be 0.5, so that'd be 50%. This situation may not seem too serious to you, but remember that in a real-world problem, and with the aid of a high-speed computer, a researcher may want to study the effect of 50 variables on the outcome of an experiment. Using a little mathematics, we can show that the study would require 1,225 separate tests. Check each pair of variables for significant difference of means. At the alpha equal to 0.05 level of significance for each test, we could expect 61.25 of the test to have a type 1 error. In other words, these 61.25 tests would say that there are differences between means when there are really no differences at all. To avoid such problems, statisticians have developed a method called the analysis of variance, abbreviated ANOVA. We will study single-factor analysis of variance, also called one-way ANOVA, in this section. With the appropriate modification methods of a single-factor ANOVA generalize to n-dimensional ANOVA, but we leave that topic to more advanced studies. If you end up getting a master's in applied mathematics, which is what I have, you will do, this is basically this section is where you pick up on your first stats class in grad school, except at a much higher and scarier level. A psychologist is studying the effects of dream deprivation on a person's anxiety level during waking hours. Brainwaves, heart rate, and eye movements can be used to determine if a sleeping person is about to enter into a dream period. 3 groups of subjects were randomly chosen from a large group of college students who volunteered to participate in the study. Group 1 subjects had their sleep interrupted 4 times each night, but never during or immediately before a dream. Group 2 subjects had their sleep interrupted 4 times also, but on 2 occasions they were awakened at the onset of a dream. Group 3 subjects were awakened 4 times, each time at the onset of a dream. This procedure was repeated for 10 nights, and each day all subjects were given a test to determine their levels of anxiety. The data in Table 1017 record the total of the test scores for each person over the entire period. This would be a really, really cool study. Higher totals mean higher anxiety levels. From Table 1017, we see that Group 1 had N sub 1 equals 6 subjects. Group sub 2 had 7 subjects, and Group sub 3 had 5 subjects. For each subject, the anxiety score, X value, and the square of the test score, X squared value, were also shown. In addition, special sums are known. We will outline the procedure for a single factor ANOVA in 6 steps. Each step will contain general methods and rationale appropriate to all single-factor ANOVA tests. As we proceed, we will use the data from 1017 for a specific reference example. Our application of ANOVA has 3 basic requirements and general problem with K-groups. Go ahead and take a moment to write these down. Okay. Step 1, determine the null and alternate hypothesis. The purpose of an ANOVA test is to determine the existence or non-existence of a statistically significant difference among group means. In a general problem with K-groups, we call the population mean of first group mu, the population mean of second group mu sub 2, and so forth. The null hypothesis is simply that all of the group population means are the same. Since our basic requirements state that each of the K groups of measurements come from normal, independent distributions with common standard deviation, the null hypothesis states that all the sample groups come from one and the same population. The alternate hypothesis is that not all the group population means are equal. Therefore, in a problem with K groups, we have, go ahead and write that down. All right, notice that the alternate hypothesis claims that at least 2 of the means are not equal. If more than 2 of the means are unequal, the alternate hypothesis is of course satisfied. In our dream problem, we have K equals 3. Mu sub 1 is the population mean for group 1, and so on. You can figure that part out. And the hypotheses are underneath. We will test the null hypothesis using alpha equal to 0.05 level of significance. Notice that only one test is being performed, even though we have K equals 3 groups and 3 corresponding means. Using ANOVA avoids the problem mentioned earlier about using multiple tests. Find SSTOT. The concept of sum of squares is very important in statistics. We use the sum of squares to compute the sample standard deviation and sample variance. Sample standard deviation, they put right on top of it. Sample variance, they put right on top of it. There you go. The numerator of sample variance is a special sum of squares that plays a central role in ANOVA. Since this numerator is so important, we give it a special name, SS, sum of squares. Using some college algebra, it can be shown that the following simpler formula is equivalent to equation 2, and it involves fewer calculations, where n is equal to the sample size. In the future, references to SS, we will use equation 3 because it is easier to use than equation 2. Sorry guys, something's going on. The total sum of squares can be found using the entire collection of all data values in the groups, where n, big N, is equal to all the little n's, is the total sample size from all the groups. All right, you guys can read that yourselves. Using the specific data given in table 1017, for the dream example, we have K equal to 3. Sugar, hold on. Total number of groups. Here's all the info. They gave you all that before. So if we add it up, we get 18. Total number of subjects. Total sum of value of x values is 156. Therefore, using equation 4, we have 134. The numerator for the total variation for all groups in our dream example is 134. What interpretation can we give? If we let x bar total be the mean of all x values in the group, then the mean of all x values is equal to the sum of the x's total divided by n under the null hypothesis that all groups of the same distribution represents the numerator of the sample variance for all groups. Go ahead and pause the video to write this part down. As we will see, SSBET and SSW are going to help us decide whether or not to reject a null. Therefore, our next two steps are to compute these two quantities. Find SSBET. Go ahead and take down the notes that you need from here. If we use algebraic manipulations, we can rewrite the formula in the following way to make it easier. Using the data from table 1017 for the dream example, we have the following. Okay. Therefore, the numerator of the between group variation is 70.038. Find SSW. Gonna take the SS total, subtract from the SSBET, so that 156, I think, minus the number we just got. Guys can write this down. Pause the video if you need to. Okay, so you're looking at SS1 equal to 23.333. So finally here, okay, it was 134. All right. Now why they chose to add these instead of just taking the 134 minus the 70. 134 minus 70.038 get you to 63.962 as well. So again, I don't know why they went around and did it this long way, but they did, so I guess you should too. In steps 3 and 4, we found SSBET and SSW. Although these quantities represents variability between groups and within groups, they are not yet the variant estimates we need for our ANOVA test. You may recall our study of the student's t-distribution in which we introduced the concept of degrees of freedom. Degrees of freedom represent the number of values that are free to vary once we have placed certain restrictions on our data. In ANOVA, there are two different types of degrees of freedom. Degrees of freedom BET representing degrees of freedom between the groups, and degrees of freedom W representing the degrees of freedom within the groups. A theoretical discussion beyond the scope of this text would show. Go ahead and write that down. You guys can see now why I made this its own video. The variance estimates we are looking for are designated as follows. Mean square between and mean square within. In the literature of ANOVA, the variances between and within groups are usually referred to as mean squares between and within groups respectively. We will use the mean square notation because it is used so commonly. However, remember that the notations MSBET and MSW both refer to variances, and you might occasionally see the variance notations S squared BET and S squared WB would be used for these quantities. The formulas for the variances between and within samples follow the pattern of the basic formula for the sample variance. However, instead of using n-1 in the denominator for MSBET and MSW variances, we use their respective degrees of freedom. Okay, so I'm sure they'll show us that. And here they go. Using these two formulas, the data of table 1017, we find the mean squares within and between variances for the dream deprivation example. So mean squares between 35.019, mean squares within 4.264. Find the F ratio and complete the ANOVA test. The logic of our ANOVA test rests on the fact that one of the variances can be influenced by population differences among means of several groups, whereas the other variance cannot be so influenced. For instance, in the dream deprivation and anxiety study, the variance between groups will be affected if any of the treatment groups has a population mean anxiety score that is different from that of any other group. On the other hand, the variance within the groups compares anxiety scores of each treatment group to its own group anxiety mean, and the fact that the group means might differ does not affect the MSW value. Recall that the null hypothesis claims that all the groups are samples from populations having the same normal distributions. The alternate hypothesis states that at least two of the sample groups come from populations with different normal distributions. If the null hypothesis is true, then the measure mean squares between and mean squares within should both estimate the same quantity. Therefore, null hypothesis is true and the F ratio is given. The F ratio is the sample statistic F for ANOVA test. Should be approximately 1, and variations away from 1 should only occur because of sampling errors. Nearly done, guys. The variance within groups is a good estimate of the overall population variance, but the variance between groups consists of population variance plus an additional variance stemming from the differences between samples. Therefore, if the null hypothesis is false, then the variance between will be larger than the variance within, and the F ratio will tend to be larger than 1. The decision of whether or not to reject the null hypothesis is determined by the relative size of the F ratio. For our example about dreams, the computed F ratio is the 35.019 divided by the 42.64, which is 8.213. Because large F values tend to discredit the null hypothesis, we use the right-tailed test with the F distribution to find or estimate the p-value for the sample F statistic. We use the F distribution table. Table requires us to know degrees of freedom for the numerator and degrees of freedom for the denominator. The degrees of freedom for the sample test statistic F in one-way ANOVA. So K minus 1 and N minus K, where N is the number of groups, where K is the number of groups and N is the total sample size across all groups. For our example about dreams, the degrees of freedom for the numerator is 3 minus 1, which is 2. Degrees of freedom for the denominator is 18 minus 3, which is 15, but they decided to put another minus in there. Sorry, guys. That should look like this. All right. Let's use the F distribution table to find the p-value of the sample statistic F equal to 8.213. The p-value is a right-tail area as shown in 1016. There's all the info for you. In table 8, look at the block headed by column 2 and row 15. For convenience, the entries are shown in table 1018, excerpt from table 8. we see the sample 8.213 falls between the entries 6.36 and 11.34, with corresponding right tail areas of 0.010 and 0.001. The p-value is in the interval between 0.001 and 0.010. Since alpha is 0.05, we see that the p-value is less than alpha, and we reject the null hypothesis. At the 5% level of significance, we reject the null hypothesis and conclude that not all the means are equal. The amount of the dream deprivation does make a difference in mean anxiety level. Note, technology gives the p-value of 0.0039. Oh, sugar. Okay. Here's your procedure requirements in the beginning of your procedure. Go ahead and pause the video so you can take that down. It continues, so make sure you pause it here as well. And then here's the last one. Congratulations, you guys have, oh no, there's more. Oh man, okay, good, here's the last of it. All right, that would be the summary of the ANOVA results. If you guys have any questions, make sure you email me. Make sure you're working on preparing for the final and working on your career project. Other than that, just get your homework and quizzes in and you're good to go.